this, we've got 100 grams of water instead. So as we're going to look at a question like this, one way to solve this one is to take your number of grams. That's what I'm going to start with. I'm going to be really specific. It's 100 grams of H2. And this is how the example that I'm going to give out has, the worksheet I'm going to give out has an example on it that looks like this kind of a setup. And I think you'll like this version of solving it. There's different ways to do it. But one way to do it is with conversion. You have to convert to moles anyway. So if we're going to convert grams to moles, I need to put grams on the bottom and moles up on top. That's moles of hydrogen. All right, so let's find the molar mass, first of all, of hydrogen. What's the molar mass of H2? 2.02, right? Because it's H2 there. Then you can just keep going with one more conversion factor. And it tells us in the equation that for every 2 moles, so in this case, think of this as 2 moles of H2 reacting. For every 2 moles of H2 that react, 571.7 kilojoules gets released. Well, I need moles of H2 to go on the bottom, so it will cancel. And there's a 2 with moles of H2. That's where I'm getting that 2 right there. That 2 is that 2. I would release. And again, the negative sign just means energy is released, all right? So
like it doesn't, like when you're multiplying across, don't include that negative?
in your final answer, you have 2 options. You can include the negative sign in your final answer, or you can get rid of it and you can just say the word released. I'm usually probably just going to say the word released because I can think about what that means, but I'll write it both ways. So let's go ahead and multiply and divide as we need to. I'm going to do 100 divided by 2.02, and I'll say times 571.7 over 2. And then, so that's going to give me 14,221. I'll go back up to what was given to me in the question. That's the data I started with. I started with 3 sig figs. So I'm going to call this 14,200. And then this is Amelia's question there. I could say 14,200 kilojoules. I know that the negative means released, or I think it's important to know what that means. So like in talking about it, I would say that number of kilojoules is released. They use the word produced in the question, so it's kind of like an understood that it's going to be produced or released. But I wanted to go over that. That's what the negative sign means. Zach, did I forget to do something?
No, I was just wondering what was, can you go over the math as well?
Yes, I will, and I think I need to do that because I forgot. No, I did divide by 2. So yeah, let's go over the math here. I wanted to check my calculations. I did 100. Anything that's on top, you multiply times. Anything that's on the bottom, you divide by.
Did you just multiply straight across and divide by?
Yeah, and you can leave out the ones too. I just kind of do that as a placeholder to talk about the process there. It doesn't matter the order that you multiply and divide in. I like to go in order though, Micah, because just in case I wanted to stop early, if I wanted to figure out how many moles do I have, maybe to use it for something else, if I go in order and do those first 2 steps first, I can see in my calculator, if I do that first 2 steps, 100 divided by 2.02, I can see I've got 49.5 moles as a kind of a step there. So I like to go in order so I can see the numbers as I go across. I think it's about to reset, huh? But you'll get the same answer either way. The most important new thing on this is realizing that the 2 moles of H2 are locked into place with the 571.7 kilojoules of energy there. Guys, any questions on that one? All right. So on that first one, what did they give us to start with? 100 grams. Yeah, grams. That was kind of my point. Good. Thanks, Shelley. We're starting with grams there. Some other questions might start with something else. What is the next question on your sheet? What does the next question give you as the starting point? It gives you kilojoules. We can still work through this in the same process using that technique. It's called dimensional analysis there. We can still use that same process. Flip screens here. Start off by writing down what's given, 5,000 kilojoules. How many sig figs are in that 5,000? That decimal's important there. Yep, yeah, that's going to give us 4. All right, so, and it says releases here. So mathematically, when I see releases, that means it's a negative amount of kilojoules. I'll talk about that after I get my answer. What would happen if you left that out accidentally? Nothing really. Well, you would get a negative. So if you could potentially, if you leave out both negatives, nothing happens. But if you include one of them and not the other, if you ever get a negative amount of grams, you just need to probably drop the negative sign because you can't have negative grams. But the negative 5,000 kilojoules means released mathematically there. So I need kilojoules to go down here, so it's going to cancel. And I'm trying to get this into grams of H2. Well, the reaction in the first conversion factor can only relate 571.7 kilojoules of energy for every 2 moles of H2. Once again, these numbers came from the chemical reaction. And then my last step is to go from moles to grams. So moles of H2 on the bottom, grams of H2 up on top. It's the molar mass step. So for hydrogen, it's 2.02. And again, not exactly. It's just backwards of what we did last time. I can see the reason I put my units where I did. I'll do 5,000 times 2. Negative 5,000 times 2 divided by 571.7 negative times 2.02. And with sig figs of 4 sig figs, we'll say I'm going to get 35.33. Multiply times numbers on top, divide by numbers on the bottom. And that's grams of H2. And that's 4 sig figs there. So if I, didn't pay close attention and I left out the word released as I read through it, and I just put 5,000 to start with, but I included my negative there, I might have accidentally gotten negative 35.33 grams. You probably just need to drop the negative sign. You're never going to have negative mass. It's like the amount of the substance. You can't have reverse negative substances or anything. You could have left out both negatives and you would have still had the right answer. So just know that the negative means release mathematically to include it, which can become important next week when we talk about some calorimetry stuff, keeping up with that negative sign. For today's stuff, the negative almost is just like an artifact that could be left out for most of the questions, as long as you understand that negative means released, positive would mean absorbed. But I like to go ahead and talk about it and start using it because it becomes more important next week. All right, so that's how you work with questions like that, and that's what most of your assignment is going to be about. The other thing I wanted to go over today was these things called energy profiles, or sometimes they're called reaction coordinate diagrams. They're a way that we can keep up with positives and negatives, endothermic and exothermic reactions. So when you have a reaction coordinate diagram, this is a way to graphically show the reaction's progress as it goes from reactants to products. And instead of just having a flat reaction like this, if you wanted to show it on a y-axis of potential energy. So when we talk about the stuff of energy, chemistry, and thermochemistry, it's really important that we really know what those words system and surroundings are all about. Those are 2 of the vocabulary words you work with system and surroundings. When you're dealing with a chemical reaction, the reactants themselves, as they turn into products, so like the molecules here, those are your system. And we can really focus on the system either gaining energy if it's endothermic or releasing energy when it's exothermic by making a graph like this. So this reaction that we just worked with in red, if it's got a negative delta H, negative means exothermic. So keep that in mind. Negative delta H means exothermic. If I wanted to represent this one on an energy profile, or it's also called a reaction coordinate diagram, we put the potential energy. So this means like the chemical, for a chemical reaction, it's the chemical potential energy that we're dealing with. All right, so potential energy is the chemical energy. We think of it as, it's kind of like stored in the bonds. That's two hydrogens bonded together. In a way, it's like how much energy do they have kind of stored in their bonds. Just like if you were to take a bow and arrow and you stretch the bow back, you know, you're putting chemical potential energy into the band on the bow. Well, with these, the energy is in the bond of the two hydrogens. So if it's a negative delta H, it means the reactant started with more chemical potential energy. So I could actually write the reactants on it. And again, I get in trouble because I leave out my solid and liquid and gas a lot, and they are important here. So the two hydrogen gas molecules, the oxygen gas molecule. The hump represents the fact that you need some what's called activation energy. Activation energy, one way to think of it is like when you strike a match, the match won't burn by itself. You have to provide a little bit of energy, so the friction of striking the match provides that energy. That's why these often have a hump. And then finally, on this side, you could actually write your specific products. I don't necessarily know where I started or where I ended, and that's common with this stuff with energy and chemistry. You may not know the exact path, but all that's important is where you start and where you ended. And that was the vocabulary word that was called a state function. I might, what's that?
That sounds like a motivational quote.
Yeah, that's right. It doesn't matter how you get there, as long as you get there. So maybe the hump is a really high hump, or maybe it's a really low hump you go over, but as long as you start here and you end there, the change in energy, so this is what we call the delta H. From the start to the finish, the change in energy was a drop of 571.7 kilojoules. These reactants had 571 kilojoules more than the products did. Law of conservation of energy says it can't be destroyed. It was just released to the surroundings. So it warmed up the surroundings. Yeah?
It kind of seems like individual atoms that like nuclear energy like produces more.
It's inside of the nucleus, there's some, not bonding there, but I don't even know what to talk about. Something keeps those protons stuck together. There's a force that keeps them together, and it's a similar idea, I suppose. Yeah, it's nuclear potential energy in the nucleus. So, exothermic, as the reaction proceeds, we would go downhill overall. Maybe there's a tall hump, maybe there's not much of a hump at all. So then you've got a couple we're going to draw on your sheet, and I'll do them on here. We just want to get the shape right and represent our delta H as we go from reactants to products. All right, so looking at the first one, nitrogen gas plus oxygen gas makes two NOs. For all of these graphs, you're always just going to do your XY axis there.
We need to label it.
We do at least label the y-axis as energy. I'll call it potential energy here. Sometimes it just says energy. Sometimes they'll say delta H on there, or just E for energy. And then the x-axis isn't a normal axis. It just means as the reaction proceeds. I'll just put Rx in for reaction. If this one's a positive 180 kilojoules, should it go uphill overall or downhill overall? Yeah, so we need to make sure you leave some room. You need to end up higher than where you started. So I'm going to start kind of low. They didn't give me any states of matter here, so I don't have to worry about them. Then you go up over an activation energy barrier, so over a hump, and we'll say 2NO. And then in the end, I just want you to recognize that we represent the delta H by that barrier. The delta H is positive 180 kilojoules. So these reactants had less chemical potential energy kind of stored in their bonds. By the end of the reaction, they've got more chemical potential energy. Where did they get the energy? They took it from the surroundings. So their surroundings probably got colder as they took in energy for themselves. All right, and next one's going to have the opposite shape, more like the shape of the first one that we drew. Sometimes they'll just say energy or E. But because the system is the chemical reactants, I like to think of it as that chemical potential energy stored inside of those bonds, like batteries inside of the molecules. This one's got to leave some room to go down. So I'm going to start at high. I'm going to end at lower. 2 sulfurs plus 3 oxygen molecules. 2 SO3. So I wanted to go ahead and take a look at some of those because we'll see those more and more, not just in this unit, but throughout the course. Oops. 4. And just a reminder, that one's exothermic, this one's endothermic, so I'll add that to it also.